Hi everyone. Today I'm presenting the paper Advancing Divide and Conquer Phylogeny Estimation using FouldsSupertrees. This work is done under the supervision of Tandy Wernau and in collaboration with Thien Lei, Sarah Christensen, and Aaron Molloy. First, we'll go over an introduction and some background of the problem. Then we'll introduce some terminologies to formally define the problem. We'll present the algorithm exact RFS and a pipeline that uses this algorithm. Throughout the talk, I will not be giving any proofs. Rather, we'll try to explain the algorithmic ideas and tell people why this work is important. We'll also present some experiment results and discuss future work directions. So when we're given a set of species, such as the bird species shown here, we use a phylogenetic tree to represent the evolutionary history of those species. Estimating such phylogenetic trees is a big problem in biology. However, unfortunately, most of the leading methods now either does not scale well or is not statistically consistent. To combat such a problem, people devised this divide and conquer pipeline that divides the set of all given species into overlapping or disjoint subsets so that we can apply tree estimation methods on the subset of species. And then once we obtain the subtrees, we can use the supertree methods to combine the subtrees into a tree on all species. The advantage of such a pipeline is that it makes phylogenetic estimation methods more accurate and faster. Such a pipeline can also be provably statistically consistent. So an important step in such a pipeline is the supertree methods. For the divide and conquer pipeline to be provably statistically consistent, we have to use supertree methods that can solve supertree problems optimally. However, current supertree methods which are most accurate are mostly local search heuristics for NP-hard problems. In particular, this talk will be focusing on Robinson-Folds supertree problem, which we will formally define later. So this is a well-established supertree problem, and it has some desired properties, such as it's close to maximum likelihood trees. It's proven to have good accuracy in terms of species tree estimation in presence of gene loss and duplication. Some current leading Robinson-Folds supertree methods include Plumist, MAL-RF, FastRFS. Those methods, like we mentioned, either uses local search heuristics or solves the problem optimally, but only in a constrained search space. In contrast, our algorithm exact-RFS2 is a polynomial time algorithm that solves the Robinson-Folds supertree problem on two binary input trees optimally without any constraint on the search space. Because this algorithm solves Robinson-Folds supertree problems on two input trees optimally, a pipeline that uses this algorithm can be statistically consistent. So here are some standard terminologies that we use. For a labeled tree T, we use V of T, E of T, and L of T to represent the vertex, edge, and leaf set of this tree T. For every edge in a tree T, it induces a unique bipartition, A and B, where A and B are the leaf sets of the two subtrees obtained from deleting E from T. We denote C of T to be the set of all bipartitions in a tree, so there is a bijection between the set of bipartitions of T and the set of edges in T. A bipartition is either trivial or non-trivial. A trivial bipartition, one side of the trivial bipartition has only one leaf, while in both sides of a non-trivial bipartition, there are at least two leaves. So for example, the bipartition L1 versus the rest of the leaves is a trivial bipartition. The bipartition induced by edge E1, which is L1, L2 versus the rest of the leaves, is a non-trivial bipartition. Given two tree T and T prime on the same leaf set, the Robinson-Fold score of those two trees is the number of bipartitions in one but not the other tree. A related measure, the split support score of two trees on the same leaf set, is the number of bipartitions shared by these two trees. As we can see, these two measures are kind of like the complements of each other. So for an example, the Robinson-Fold score of these two trees T and T prime is 4 here because the two bipartitions induced by E2 and E4 are in T but not T prime. The two bipartitions induced by E6 and E8 are in T prime but not T. The split support score of these two trees is 9. So first of all the trivial bipartitions are present in both trees, so there is a score of 7. Also, the bipartition L1, L2 versus the rest is induced by E1 in T and induced by E5 in T prime, and the bipartition L5, L6, L7 versus the rest is induced by E3 in T and induced by E7 in T prime. So those two bipartitions are also present in both trees. So a total score of 9 between T and T prime. Given a tree T and a subset of leaves, we say the tree T restricted to this subset of leaves is the minimum spanning subtree on this set of leaves X with degree 2 vertices suppressed. For example, let's take a look at the tree T here. If we set X to be the leaves L1 to L7, then we obtained T restricted to X on the right by first ignoring the leaves not in the subset and then suppressing degree 2 nodes, turning each path into a single edge. With this definition, we can extend the Robinson-Fold score definition of two trees to trees with not identical leaf set. That is, for two trees T and T prime where they have a shared leaf set X, the Robinson-Fold scores of T and T prime is defined to be the Robinson-Fold scores of T restricted to X and T prime restricted to X. Next, we define our Robinson-Fold supertree and split-fit supertree problem formally. We're given a profile A of n source trees T1 to Tn, where the leaf set of Ti is Si, which is a subset of S that represents the set of all species. And we want to find a binary supertree that optimizes some criterion. For the Robinson-Fold supertree problem, we want to find a binary supertree with minimum sum of Robinson-Fold scores with respect to the source trees. Similarly, in the split-fit supertree problem, we want to find a binary supertree that maximizes the sum of split support score with respect to the source trees. As we mentioned before, Robinson-Fold scores and split support scores are a complement of each other, so it doesn't come as a surprise that minimizing Robinson-Fold scores and maximizing split support scores are equivalent to each other. Here are our theoretical results. The first theorem basically says that for any input set of source trees, Robinson-Fold supertree problem and split-fit supertree problem are equivalent. Our second theorem states that the algorithm exact RFS2 can solve the Robinson-Fold supertree problem and split-fit supertree problem on a input set of two source trees optimally in polynomial time when the two source trees are both binary. We also have a hardness result that states that the Robinson-Fold supertree and split-fit supertree problems on three source trees are NP-hard. Next, we present our algorithm exact RFS2 and a divide and conquer pipeline that uses this algorithm. We introduce a few more notations. So two bipartitions are called compatible if and only if they can coexist in one tree. It's also proof that two bipartitions A, B, and A prime, B prime are compatible if and only if one of A and B is a subset of one of A prime and B prime. So for example, the bipartition induced by edge E1 is compatible with the bipartition induced by E7 because L1 and L2 is a subset of L1, L2, L4, L3. In comparison, the bipartition induced by E2, which is L1, L2, L3 versus the rest, is incompatible with the bipartition induced by L6, which is L1, L2, L4 versus the rest. We differentiate between two kind of structures from the input trees T1 and T2. We call the input trees T1 and T2 restricted to their shared leaf set X, the backbone trees of T1 and T2. And we call the rest of the input trees the extra subtrees. Let's take a look at the example here. So the backbone trees of T1 and T2 are highlighted in bold, and the extra subtrees are painted in blue. Even though the extra subtrees A1 to A6 and B1 to B6 are shown as leaf here, they can actually represent a complicated subtree. With the notation introduced, we give a very high level idea on the algorithm. In the first step of the algorithm, we compute the backbone trees T1 restricted to X and T2 restricted to X. And then we compute what we call a weighted incompatibility graph on the bipartitions in the backbone trees. We will formally define this weighted incompatibility graph later when we go through the example. Next, we compute a maximum weight independent set on this weighted incompatibility graph. So this max weight independent set would represent a max weight compatible bipartitions from the backbone trees. Next, we construct a trivial supertree T and then add each bipartition from this independent set to the backbone of this supertree. At this point, if the supertree is not binary, then we arbitrarily refine T until it is binary. Now let's go through a detailed example to see how this algorithm looks like in action. We're given two trees T1 and T2, where the leaves of T1 are L1 to L7 and A1 to A6. The leaves of T2 are L1 to L7 and B1 to B6. So the shared leaf set is L1 to L7. The backbone trees of T1 and T2 are bolded. For any edge in the backbone trees, we associate a path with it and then use the length of the path to define the weight of that edge. For example, for the edge E in the backbone of T1, it corresponds to an edge from V1 to V4 in the original tree T1. So it's a path of length 3, which means the weight of edge E would be 3. The meaning of this weight is such that if we add the bipartition induced by this edge E to the backbone of the supertree and then attach the extra subtrees appropriately, then the supertree can include at most 3 bipartitions from T1. That is the bipartition induced by the 3 edges on the path corresponding to E. Now we define the weighted incompatibility graph formally. For edges E1 to E8, let them induce the bipartitions pi1 to pi8. We see that each bipartition pi1 to pi8 from the backbone trees becomes a vertex in the incompatibility graph. And there's an edge between two vertices if and only if the bipartitions they represent are incompatible. For example, Pi2 is induced by edge E1. It is the bipartition L1, L2, L3 versus the rest. Pi6 is induced by edge E6, and it is the bipartition L1, L2, L4 versus the rest. These two bipartitions are incompatible, thus there is an edge between the vertex Pi2 and Pi6. For every vertex in the incompatibility graph, the weight of the vertex is the weight of the edge that induces the bipartition. For example, Pi1 is induced by E1, and E1 corresponds to a path of length 3 in the original graph, which means the weight of E1 is 3, which means the weight of Pi1 is 3. Similarly, E2 corresponds to a path of length 4, thus Pi2 has a weight 4. So once we construct the weighted incompatibility graph, we compute the maximum weight independent set in this graph, that is, the maximum weight set of vertices such that there is no edge between any of them. In this case, because there is no edge between any two vertices, all those vertices represent compatible bipartitions. In particular, in this example, the max weight independent set includes Pi1, Pi2, Pi3, Pi5, Pi7, and Pi8, with a total weight of 15. We will not get into the details of how to use the computed compatible bipartitions to construct the supertree, but the overall idea is that we start with a initial supertree that doesn't share any bipartition with the source tree T1 and T2, and then we refine it gradually using the bipartitions from the independent set we computed. Recall that the max weight independent set computed contain bipartition Pi1, Pi2, Pi3, Pi5, Pi7, and Pi8. We add them step by step, starting with Pi2, Pi8, and then Pi1 and Pi5, which is the same bipartition, and Pi3 and Pi7. In each step, we refine the backbone of the supertree to contain those bipartitions from the backbone of the source tree, and then move the extra subtrees appropriately. Next, we describe a Dactyl-like pipeline that uses the exact RFS2 algorithm as the supertree method. First, when we're given a set of source trees, we estimate a starting tree T using any statistically consistent method. And then we find a centroid edge E and P leaves closest to E in the 4 subtrees obtained from deleting the edge E and its endpoints. We let A and B be the bipartition induced by the edge E and define S1 to be A union P and S2 to be B union P. Then we restrict all the source trees to the leaf set S1 and S2 separately and estimate the subtrees T1 and T2 on the leaf sets S1 and S2 respectively. In the last step, we use exact RFS2 to combine the subtree T1 and T2. We prove that this Dactyl-like pipeline is statistically consistent as long as the method we use to estimate the starting tree and the method we use to estimate the 2 subtrees are statistically consistent. Besides the algorithmic and harness results, we also performed experiments. In the first experiments, we are given a set of K gene trees on 501 species with varying value of K. And for each value of K, we did 10 replicates of the experiments. In each replicates, we used the Dactyl pipeline plus either exact RFS2 or fast RFS as the supertree method to estimate the species tree. And then we evaluate the estimated species tree in comparison to the model species tree in terms of RFS score. So for RFS score, the lower is the better. As we can see in the graph, for each value of K, exact RFS2 performs better than fast RFS. In particular, when k equals 1,000, exact RFS2 strictly dominates fast RFS. In the second experiment, we're given a set of k source trees on subsets of the 500 species of a model tree, where k can vary from 2 to 14. The methods we use here is greedy RFS and fast RFS, where greedy RFS is just using exact RFS2 repeatedly on 2 trees until we're left with only 1 super tree. The order in which we choose the trees to apply exact RFS on is just the greedy order, where we choose the 2 trees that share the most number of leaves first. In the end, we evaluate the estimated super tree with respect to the model tree in terms of RFS score. And then we repeat this experiments for 10 times and compute the percentage of times in which greedy RFS performs better and the percentage where fast RFS performs better. We can see from the graph that when the number of source trees is small, greedy RFS can be strictly better or ties with fast RFS. But as the number of source trees increases, there is an advantage of fast RFS. There are a lot of future directions that we can explore for this project. First of all, we can do more experiments with the Dactyl exact RFS2 pipeline in comparison to other leading supertree methods. We can also do experiments on different data sets. Another direction is we can try different greedy strategies for the greedy RFS algorithm. To complete the work, we can also do more experiments and analysis on the running time of the algorithm to show the practicality of the algorithm, especially on large data sets. That's all from me. Thank you.